Before we continue with the remaining scheduling items, do you still have any questions for what we have done for dependent tasks? Deadline adjustments, aperiodic tasks.
So, the only form of dependency we looked at was when they were to require the same resources.
Yeah.
No, maybe there are like order dependencies, or is that maybe that's so just one task? Are there other kinds?
Your question being what exactly?
Are there other forms of dependent tasks?
Other form of dependent tasks other than just sharing resources? Yes, but I can logically translate all of these dependencies into something like that. The other big area of dependencies is direct message passing, which is a little simpler because you have to actually get both tasks responding at the same time. But that's the other family of synchronization items. And there also can be logically translated something like that. Or the other way around, you can also translate all of them into message passing, which if you want to run this through a logic analyzer, then you would actually rather go this direction, that you translate all of your shared memory-based operations into message passing operations. Your theory improvers will be able to handle message passing easier than shared memory operations. Why?
I was just curious.
No. Why are your theory improvers easier able to handle message passing than shared memory?
There are no strict conditions on who can access shared memory.
You already made lots of constants and copies in the process. The moment you go to shared memory, you go to message passing interfaces, what you do logically is you translate all your communications by I make a copy of something and hand over a copy to somebody else. That's at least the strict form of message passing. I'm not talking about handing over a pointer to somewhere else. This is, of course, banned in that kind of environment. It should be banned in general. It's a pretty dodgy thing to do message passing. So message passing interpreted as you make a copy of your current allocation, of your data allocation, and you only hand over a copy. That makes memory management, logical consistency a lot easier. You basically live in the world of functional programming. Because everything you get in from a message passing interface is automatically a constant. And it's a very different and much easier to handle concept than mutable shared memory. I guess everybody, welcome to the bit more strongly built people. Everybody gets this distinction between message passing and why message passing is logically a little easier to handle. That's great. Okay. Other task dependencies, the discussion about scheduling and task dependencies has been sinking in. You convinced yourself that, yes, there is a way how you can schedule things in order which avoids deadlocks completely. Okay, cool. Then, preemptive scheduling. Why would you want to do preemptive scheduling? Okay, what is preemptive scheduling? What you do is you divide all of your tasks into blocks which are not preemptible, non-interruptible blocks. And you, by the definition of these non-interruptible blocks, if you're at the end of a non-interruptible block, you become interruptible. And you say so or indicate to a scheduler that please, if you like to, you can preempt me now. I'm happy to release my resources and release the CPU particularly. So far, so good. We also assume that all critical regions are completely enclosed into one of these non-interruptible blocks. You cannot hold resources beyond that point. Cool. What does that mean? Why would you do something like that? What is the first obvious advantage? by looking at this item on the screen. What about deadlocks? How do you prevent deadlocks in cooperative scheduling?
So if the scheduler is going strictly like that, where it only switches a task when it says it can, it means that you can have all the stuff where you'd be worried about deadlock forming in a single block where it can't be interrupted.
Mm-hmm.
So they'll prevent deadlocks.
Yeah, there are no deadlocks. You cannot possibly create a deadlock if you throw the job of using the resources and releasing the resources into one block. One task can do it at a time, and you have to release the resources by the end of it. Okay. Deadlocks are gone. Nice. Any price to pay for that? Or give me other advantages first. What are other advantages of doing it like that? How do you feel about cooperative scheduling from a perspective of real-time systems?
Seems to kind of go against the philosophy.
Against the philosophy?
Real-time systems where you only task switch if you have a higher priority task.
Yes. But you can also still switch to the higher priority task. You just switch at a different point in time. This doesn't imply any kind of round-robin scheme. Just say you let this task complete, and then when it yields, you can switch to the highest priority, which is currently runnable. Does that go against the real-time philosophy?
I have to switch 4 units.
You may have to switch what?
4 units.
Yeah. Well, it depends on the blocking times, which we are doing now. In terms of predictability, how do you feel in terms of predictability if you schedule like that? Is that more predictable or less predictable? It can be more predictable.
It's like you can just say every task gets like a second, and a second, and a second, and a second, because if they're interruptible blocks, it's just about 2 minutes.
Okay. That sounds like an easy to calculate latency. If I know that the worst thing that can happen is that all the lower priority tasks will complete their interruptible section, and it's my turn. Or all the higher priority tasks, of course, will complete their non-interruptible section, then it's my turn. If they're bound or known or the same, it seems fairly easy. Now, one thing which is interesting is you don't have preemption, which means the number of task switches is quite likely smaller in that process. You have to guarantee a fairly large chunks of code to be running consecutively without anybody touching them. In terms of predictability, that gives you a whole range of new dimensions of predictability. For example, your cache usage all of a sudden becomes a little bit more feasible to calculate what that means, because you know that from the beginning of this operation to the end of that, this will be staying in the CPU, which means if there is any benefit of my caching here, it will work, and it will work every time like that. As opposed to you have preemptive scheduling, you just started that little piece of code, then somebody else comes in, all your caches are... In terms of predictability, that's harder. Plus simply the fact that you have smaller numbers of task changes is already interesting. Okay? That seems like an interesting alternative. Predicting execution times. You have larger atomic blocks, your granularity is much larger. You can calculate with these gigantic blocks which we are scheduling here, and if you have some reasonable estimate how long that takes, it will always take that long because they're uninterrupted. That can make it much easier to predict your worst case execution times. And as a nice side effect, we are deadlock free by design. Schedulers don't even have to handle interrupts. Schedulers become just a function call somewhere. Interesting. Okay, what are the downsides? You have to wait until task will voluntarily surrender the CPU, so slightly longer delays potentially. Okay. Now the definition of slightly longer, because in real-time systems we're not dealing with we have to be the fastest, we are dealing with predictability. So as long as you can predict this maximum delay in a sensible way, there is no harm done. It can be in absolute terms longer, but I'd rather run a system which in absolute terms has a longer latency, but I can predict it exactly, rather than a system which has a shorter latency, but may depend a little bit. Other nasty, annoying side effects. Come on, the most obvious one. Yes, cooperative scheduling. What if a task doesn't cooperate? Exactly. So just like with standard student population, how many of a student in a 500 student class are not the friendly guys? So you will have a certain number of, you have a certain chance that some of your tasks will maybe not collaborating. What happens if they're not collaborating? Yeah, it was a crooked metaphor. Because you, of course, have it all under your control. It's all your tasks in that sense. Yeah, of course. I was trying to write a little bit the non-cooperative angle that some single task is not cooperating. But it could also mean that, for example, some task is stalled because it was delayed due to an external signal which didn't come, which was expected, and it was unforeseeable. What do you do then?
Well, if that's the case, would it be a good idea to put it in a block like that? Or if that were all my knowledge of it, I wouldn't have put it in things that
Yeah.
get stored up in a block where
Yeah. Hence I formulated it, if assume that an unforeseeable delay happens. Of course, all foreseeable delays you put somewhere else. But assume that something unforeseen happened there. Is your system just doomed? Is your system just dead? In practice, these cooperative scheduling systems have something like an emergency watchdog. So there is an emergency preempter, which will always be reset, like running a train engine of some sort. You constantly have to indicate that everything is still fine, everything is okay. And if you're not doing this on a regular enough basis, then your watchdog will trigger eventually and will call this specific task to order, kick it out. So usually you have as a fallback, fault-tolerant operation, some kind of a preemptive system on top of that, some kind of a watchdog on top of that. Could you imagine that you have a system like this in any of your devices? Do you want to have this in your laptop, your phone? You don't? Can you imagine that anybody came up with a crazy idea of doing that? Cooperative scheduling.
I mean, there are forms of it in corporate threads, which you run your own scheduler that you run, which runs in a single thread and has its own threads that it's supposed to run.
Yeah, yeah. There are forms of that which are actually available for local library implementations. Can you imagine that somebody wrote a whole operating system based on that concept?
I mean, I think there's something that runs on Node which uses that concept, but it's a bit of a joke operating system.
Well, that choke operating system was the Apple operating system until the year 2000. The original macOS all the way until macOS version 9 was completely cooperative. Why have they been doing that? Because the Apple guys are crazy? Why have they been doing cooperative scheduling? Yeah. Sure. Anything else?
They have uniform hardware.
They have what?
Was the uniform hardware every machine?
Yes, but how is that related to cooperative scheduling? You mean less surprises?
Yeah, maybe if they had more control over the entire environment, it would make sense.
Yeah.
Yeah.
Yes. So you have to remember at what times these kind of desktop operating systems have been written. And this was at times when your CPU had spectacular, mind-boggling frequencies like 4 megahertz. And so you could count the machine instructions going through and welcome them by handshake individually while they have been going through the CPU. And context switches and keeping everything in the air at the same time was noticeably slower. Now, admittedly, not until the year 2000, but that was one way. What was the way out of this one? Yes, there was also an emergency watchdog timer somewhere in the background. And the user simply had actually a button to get it out of it. Just had an actual hardware interrupt on the side of the machine, bonk, to keep that thing in case that one task is getting a bit CPU happy and not letting loose anymore. So that was possible as well. The earlier versions of the iPhone were not very far from cooperative scheduling. There was not any multitasking happening in the sense of what you're used to now. There was actually close to nothing happening in the background besides a handful of I/O handler and drivers. Everything else was actually this one task which is going to the CPU, is owning the CPU, doing its stuff there. Why have they been doing that? Same rationale. Because the CPU power for earlier phone models was just limited enough that they said, well, I want to have more snappiness, more responsiveness for these phones. And that actually worked for many years. If you're old enough to remember the early side-by-side comparisons between different phone models, there was a quite noticeable snappiness and responsiveness difference between these models. It was exactly because of that.
What happens if like, you're doing something and it's in the floor, you kind of dropped it, and you get a phone call? Does the phone call just cannot get through since the line's
No, of course there was a very limited number of callbacks and interrupts which were enabled in there. But it was not a general multitasking that, I don't know, your game in the background can actually constantly progress the simulation while you're doing your mail, for example. This was physically impossible. You switched from your game to your mail, your game was frozen. While, of course, your phone calls are still going through. So there were these things, but what annoyed, of course, the developers is that this was not in the control of the developers, so Apple actually put his foot down that this, and this can interrupt you, nothing else. Okay. So it is not strange, even in the desktop and phone community, to think in those terms, and it kind of worked as well. It was not that it was completely unfeasible. And in the real-time environment, this is actually much more frequently used for reasons of simplicity. Because in really hard real-time environments, one thing you try to avoid, namely interrupts of all sorts. interrupts are notoriously harder to embed and to logically verify compared to sequential operations. So if you want to verify your stuff, if you want to prove it down to CPU cycles, you probably want to avoid interrupt operations.
So as part of logically verifying and systems and stuff like that, how do you do that when you're going to query code over that? Like, how do you verify a system when you're using DMAs and stuff like that?
You basically don't. If you go down that path, you're also not only disabling all the other tasks which are running, you also enable all the other concurrent hardware operations which could interfere with you at the same time. Depends. I mean, DMAs, verifying DMAs, as long as you can, for example, guarantee that there is no CPU bus collision between your DMA and your standard operation, if you can prove that, then you have separated the concerns completely and there isn't any further interference there. Then it's okay. But many other operations like, I don't know, complex timer operations in your controllers could be more boring in that context. There's a general notion, if you want to verify something completely, you actually fall back to CPU designs from von Neumann's days, trying to avoid all this modern fancy stuff like caching and concurrent background devices and operations. You try to minimize it further and further. You can actually count CPU cycles.
On the old CPUs, can you not get a new CPU and disable all the caches, all the fancy stuff? And unless they wired it wrong.
Amazingly enough, there are quite a large number of CPUs where you cannot disable that. But yes, for some embedded systems, for some ARM environments, you can actually disable that. There has been a transition phase which was pretty funny, where caches were so promoted that you didn't have any alternative anymore at all. It was beginning of the 2000s sometime, when all current CPUs had built-in level 1 caches and then all kind of cache structures. And you couldn't disable them. And then NASA was actually posting to all hacker forums they could possibly find, if you still have a 68,000 CPU somewhere, we need more of them. We're running out because they're not producing them anymore. And those are actually those cache-free, completely predictable systems which they have been building their early designs on. And they were just actually running out of design. So it was sweet when you then saw some hacker crawling through the garage of his dad, getting an old Apple II out of the garage and donating that to NASA. So we had that phase, but now we can also find CPU models which can disable that. Plus we have so much more flexibility in CPU design anymore. The fact that this specific CPU is not manufactured anymore is actually technologically today not stopping you anymore. You do your own. For any kind of a large-scale operation, this is not a problem anymore. You could just design and reconfigure CPUs for your specific device. If you're really on the cheapskate, you can download a soft processor into an FPGA. Yes, it's slow as heck, but it is completely in your control. So if you nowadays are really pressed for a CPU which is of a specific design, you can make somebody manufacture it exactly to those specs fairly easily, or you can just download it into a gate array of your choosing. Minus some speed, but that's not the concern. You want to have full control over it. Yeah.
Fairly easily, thousands of dollars does it cost to take out?
Well, I didn't buy any yet, but considering that I honestly would need to take too wild a guess to actually give you a decent answer for that. I would need to look that up. Yes, it will not be in the hundreds of dollars, but it will also not be in the hundred thousands of dollars. So it's not that far of a stretch. Okay. So, what else? What happens to the response times if we do cooperative scheduling? You love response time analysis, right? Response time analysis for cooperative scheduling is refreshingly simple. You just go through all the non-interruptible blocks of all of your higher priority tasks and see how often they can interfere with you. That's very close to what you have been doing in fixed priority scheduling response time analysis as well. But here you can pull a few more extra tricks, namely that if you manage to assume that all of your CPU times, your block times, are the same, that you just say that, as you suggested earlier, all of my tasks take 1 second, all of my blocks, well, maybe not 1 second, maybe say 50 milliseconds. And then your scheduling and your response time analysis becomes really, really simple, because everything is just a multiple of 50 milliseconds. Easy peasy. You don't have to exhaust that. You can just say that the maximum allowed non-interruptible time for any task is 50 milliseconds. Calculate, make sure this is the case. And then the rest of your response time analysis becomes really easy and straightforward. Not attractive? Little attractive? Not really convinced yet. Okay. And then you can do something really crude. In the last line, you can also say that all of my cycle times are the same too. That's maybe not necessarily practically always the case. But if you can do that, then the whole of your response time analysis falls down to you just add up all the blocks on the higher priorities, and they're all the same anyway. So it's all the same 50 milliseconds, which you assumed as your block size for your system. That means you just count down, depending on your priority, there's so and so many 50 millisecond blocks which can interrupt you. Cool, huh? So if you can design your system like that, why wouldn't you simplify your system down to that level? And then you can explain to your customers that, well, I've done my job thoroughly. This is the analysis. I can guarantee that fairly easily, without any complex scheduling analysis, deadlock analysis, etc. All of that went away by definition. Cool. What do we need to do? Everything has to be very carefully divided in these 50 millisecond code blocks, or however long it is. Usually you have protection against misbehaving code blocks. And you need to be able to design a system where actually nothing happens faster than those 50 milliseconds. Because this is the minimum delay response time, which even the highest priority task has to accept. Shown in tech. So that kind of granularity you have to actually buy into. Okay? Cool. Then the next point is worst case execution times are not completely known. Introducing a little bit of fault tolerance. We'll do a whole chapter of fault tolerance, but here in the context of scheduling, we can see how we can embed some level of fault tolerance directly into the response time analysis for our schedulers. How does that work? The left side of this one is the response time analysis which you are familiar with. And then you add something which is related to the recovery times in case you have a fault. This is the CIF, which is responsible for error recovery, which for example, could be the CPU times of your exception handlers. If you have some emergency exception handler someplace, you put those CPU times in that additional analysis. This can happen occasionally. Now you need to make an assumption how often this can happen. You need to give a guarantee that there's a minimal inter-arrival time between faults. Okay, that's not the case. If your system can permanently put its foot down the exception button and you just fall from one exception handling to the other, you cannot guarantee anything, obviously. You have to guarantee this only happens so and so often. And then you can do that. Depending on which priority the exception handling happens, we have two cases here. The first one is that exception handling happens on the same priority level. And the other one is exception handling is happening on the highest priority level. If that's the case, then all of your tasks have to consider exception handling of everybody else, regardless on which priority level. Because even the lowest priority task could have this exception handling facility needing and escalate to the highest priority, interrupting you possibly. Okay. This is all what I want to do at this time about fault tolerance. We'll talk about fault tolerance on a much larger scale in the last chapter of the course. How do you handle fault tolerance in large-scale realistic systems, like, for example, airplanes and things like that? What additional means do you need to do that? Okay, this was all about scheduling. There's one additional thing. We assume that tasks are coming on a regular basis and are released at once or released at a certain pattern. Now, there is a possibility if something is not schedulable at the moment, you could make it schedulable by having a very specific delay pattern for all of your tasks. So this task squeezes in just there, this task squeezes in just then, and the whole system may become schedulable if you have the right set of offsets for all of your tasks. From a theoretical aspect of schedulability, that's true, but this is also an NP-hard problem to do that. This is not something you can possibly do online in any way. And what you usually try to do is you go the opposite direction, you simplify further. You try to make your cycle times not random and completely independent. You try to make your cycle times based on the common denominator. So they're all factors of my minimal cycle time, or they're all powers of 2 of my minimal cycle time. Then the overall scheduling will become obviously significantly more easy. Yeah. As opposed to all your cycle times don't share anything to be divided by. They're all completely independent. That's the case, your schedulability analysis is significantly more complicated. Okay. This is just for completeness. Now a little bit for language support. What do you have in Ada? To support those kind of scheduling environments, we have task as well as inter-priorities. We have a bunch of task attributes, priorities, entry queues, priority ceiling locking, a few versions of that. The one which you saw in the lecture here is the one which is activated by default. Schedulers, you have FPS schedulers defined with a whole bunch of different priority ordering schemes defined on them. You have earliest deadline first defined, and you actually have round robin defined since 2005, I think. Or was it 2012 that round robin came in? Anyway, I don't think a lot of people will be using that in a real-time environment, but yeah, you can switch to round robin if you really like to. You also have task execution time measurements. Doesn't work on your boards, but the full-scale ADA standard defines that as well. That means you can count how much time has a specific task used in the CPU. If that's of any relevance for your overall system design. As I said, in practice, this is often tunneled by the runtime environment where you have tasks doing jobs for other tasks because it avoids task switches. That violates often your calculation of CPU accounts or makes it really complicated to do that. Ada doesn't have sporadic servers. You have probably all seen this part of the system module by now, that this has to be defined in all of your ADA environments. You have any priority and priority as two types, and basically any priority is the standard range of priorities plus the interrupt priorities at the end of it usually. So interrupt priorities are always higher than task priorities, surprise. And well, if you're not living in a strict high integrity world, then you also have functions like set priority and get priority. If you have that, what can you do if you can set the priority of a task at runtime? Write your own operating systems, yeah. Write non-predictable systems, okay, randomly assigned priorities. Yes. But you can, if you have this ability, you can also write any scheduler you want. Because the moment you have control over task priorities at runtime from your favorite task, which you may call the scheduler, then this scheduler has, of course, full control on who will be coming next in the CPU. And this scheduler can then decide anything about that, and any kind of scheduling algorithm can be implemented once you have access to the task priorities, even though the runtime environment looks at it like this is a fixed priority scheduling scheme, but it's not that fixed because your scheduler is changing the priorities all the time and can manipulate this and merge this into any operating system you want. Okay. Again, it doesn't work on your board because you're not allowed to change priorities dynamically in a high integrity system. Okay. What do we have in POSIX? Again, we have thread and interrupt priorities, which can also be dynamic. We also have priority ceiling locking, and we also have schedulers. And we do actually have sporadic schedulers in the POSIX environment. We don't have earliest deadline first usually. At least not that I have seen that. And the famous POSIX timers. As always, the last feedback, if nothing else works, you can use some POSIX timer to wing it for you. Okay, that was an overview of scheduling techniques. Did you develop a little bit more of a feel what scheduling is about? That's great, okay. And some hooks and some keywords that you can actually look from there. If you are now asked what kind of scheduler do you want to run, I think you have a bit more of a background to select something and to find out how you can parameterize that, what it means for predictability, for deadlock analysis, for interacting tasks, etc. Any further questions about scheduling?
So the cooperative scheduler part, can the granularity for each task be different?
Sure.
And the granularity for within one task? Sometimes
yeah. That was the most general equation, what you saw on top of this slide about cooperative scheduling. There it was assumed that you have any kind of block granularity flexible, and it just makes the whole analysis more complicated, but of course you can in principle do that. Yeah. I mean, there was not this kind of agreed granularity besides an overall maximum granularity in the early Mac operating systems either, for example. Just assume that there is a total maximum time. If you're not yielding after that time, that's not okay. Everything else is in your control. It wasn't exactly a real-time operating system, but yeah. Any other questions about scheduling? Want to submit a paper to the next real-time scheduling conference? It has two charming effects of that. One is it has a direct real-world effect if you do that, but also it actually appeals to the whole logic community because you can prove and verify a lot of things in those scheduling environments quite nicely. It's a nice bridging of real-world activities and strong high-integrity logic approaches.